Hello. We're going to just have a short discussion here about nuclear reactor systems. Now, as I'm sure you guys are aware, we divide the different reactor designs into generations based on the technology that they used and when they were developed. The early prototypes, of course, are Generation 1. These were some of the first commercial reactors. The Generation 2 represents most of the commercial reactors in operation today, pressurized water, boiling water reactors, and CANDU reactors. Generation 3 are some of the advanced light water reactors that have been developed over the last decade or so, CANDU, EPR, ABWR. And then Generation 3 Plus are the evolutionary designs currently under development, under licensing consideration, like AP1000, the ESBWR, and so on. And then Generation 4 are the revolutionary designs, some of the things that are going to use radically different technology from the light water or heavy water reactors that are prevalent today. Sodium fast reactors, gas fast reactors, very high temperature reactors, MSRs, that sort of thing. Now, as we talk about these reactor designs, we're going to look at them from a little bit of a heat transfer perspective, and we have to consider a few things. The first thing is the nuclear steam supply system, which is basically the nuclear fuel and everything that's used to generate steam. So in a PWR, that would include the fuel, the pressure vessel, the steam generator, the reactor coolant pump, and so on. Then the balance of plant is everything else, the turbine, the feed water pump, the condenser, and so on. Now, there are many key parameters for reactor design that are going to be influenced by heat transfer and the heat transfer calculations that we're going to talk about in this course. The obvious one is the core and the fuel design. The core has to be designed in such a way that it can be cooled and that the fuel won't melt. We also have to look at the steam generators for pressurized water reactor or various other designs so that they can remove all of the heat generated by the core and transfer that heat to the power generation side. We're also going to have to look at heat transfer in turbines. In the turbine, the steam is expanding and it can condense, so we have to look at the heat transfer behavior there. And turbines and generators can produce a lot of heat by friction. They're spinning very, very rapidly. So we also need to look at the ability to cool those systems and make sure they don't overheat. And then the condenser, of course, is where the steam is condensed back into liquid for recirculation to generate more power. So we have to look at the convection and condensation heat transfer there. As we're looking at some of these systems and how to design them, there are some key thermal design parameters that are going to affect our design. And the first one is the primary coolant temperature. The hotter the coolant, the more corrosive it's going to be. But hotter coolant also helps boost plant efficiency, so there's a little bit of a cost trade-off there. The primary coolant temperature is also going to determine your materials and design requirements. The primary coolant inventory is also an important thing. This is how much mass of coolant you have in your primary system. The primary coolant is a heat sink during accident scenarios. It can absorb a lot of energy. So knowing how much coolant you have is going to affect the progress of any accidents that may occur. And finally, you have to look at the system arrangement. When different components are at different temperatures, they're going to have varying thermal expansion. So you need to look at how those temperatures are going to be distributed to look at thermal expansion and thermal stresses. And then you're also going to have natural circulation in the system. Especially during accident scenarios, natural circulation is very important. So you want to make sure that your system is designed in such a way to take advantage of that to help maintain reactor cooling if something would happen and your reactor has to shut down. So we're going to start our look at different reactor designs by looking at the pressurized water reactor. Now, in the United States, companies like Westinghouse, Combustion Engineering, Babcock & Wilcox, and Areva are selling pressurized water reactors. These kinds of reactors are cooled and moderated by light water, pressurized to about 2,200 psi, or about 150 bar. That high pressure means very expensive components. Now, these reactors were among the first commercial plants because of their history as naval reactors, and they also have a very compact core design. The fuel-to-coolant ratio is about 1. Now, they have an indirect cycle. They transfer heat to a primary coolant that never boils and use that to transfer heat to a secondary coolant that boils and then produces energy, electricity. So this is a little bit less efficient than a direct cycle and requires some additional components, but the benefit is that there's no radioactive coolant through the secondary system, which means you don't have to have additional shielding. As far as heat transfer, we have to look at the expansion of the steam in the turbine and the convection in the condenser, and also the behavior of the feed water pump. Now, typically a PWR is a 4-loop design. There are 4 loops for the coolant to go through. Each loop has a steam generator. On one loop, you have a pressurizer. And then, of course, you have coolant pumps, at least one for each coolant loop. Now, there are also 2-loop designs from companies like B&W, but most Westinghouse reactors are 4 loops with 4 steam generators. Here, we're looking at the heat transfer in the pressurizer, the boiling and condensation behavior that is used to maintain pressure in the system. And we're also looking at heat transfer through the steam generator. So you have convection on both sides. You're going to have boiling on the secondary side, and then you have conduction through the steam generator tubes. You also have a number of safety features: emergency core cooling to inject cold water, suppression pool to help condense steam and reduce pressure, and things of that nature. Now, inside the pressure vessel, where the core is, mostly we're talking about convection from the fuel to the coolant. And here, power control is usually used by boron shims, chemical shims, rather than control rods for a PWR. Finally, if we get all the way down to the individual fuel bundles, here we're going to have heat generation in the fuel due to the fission chain reaction. And once that heat is generated, it has to conduct through the fuel and the cladding. And once it reaches the outside of the cladding, it's removed by convection or boiling in the core. So traditional PWRs, Generation 2, were constructed by mostly Westinghouse in the United States, but also B&W, Combustion Engineering, and so on. Right now, Westinghouse has developed the AP1000 plant with enhanced passive safety and a simplified design. The idea here is to reduce cost and improve the economic viability of the plants. So there's a link at the bottom of this slide that has a short video where you can look up some information about the AP1000. Next, I'm going to talk briefly about the BWR. These are sold by General Electric in the United States for the most part. And they're cooled and moderated by light water, just like a PWR, but here the pressure is only about 1,050 psi. So in this case, we allow boiling in the core, and that steam is directly used to turn the turbine. This helps improve reliability and efficiency. However, it means we have radioactive contamination of the steam running through the turbine and the condenser, so those systems have to be shielded to protect the personnel. It also helps that the flow requirement through the core during an accident is quite low. Because of the boiling, that heat transfer is very effective, so we can maintain cooling even at very low flow rates. And this is just an example of the actual layout of one of these BWRs. This is a Mark II BWR from General Electric. And you can see the distinctive upside-down light bulb shaped containment there. The reactor vessel itself has jet pumps that circulate the water, the coolant. And you have some mixing behavior, some flow and heat transfer behavior in the steam separator and the dryer. You also have boiling in the core, and so on. And then in the steam line, we have to worry about heat loss and condensation because any water that condenses in the steam line will try to fall backwards into the core, so you have some countercurrent flow behaviors and things like that. We also have some important safety features here: steam isolation valves, the suppression pool, and then some safety relief valves in the emergency core cooling system. The fuel here, you're going to have the heat generation in the core from the fission chain reaction, and the conduction and then convection. However, in a BWR, we use control blades, which are kind of shaped like an X rather than control rods. And these actually have to enter from the bottom of the reactor because the steam separators and other components are above the reactor and the control rods can't move through those. And then here we also have a fuel can on each bundle, and that's important because it restricts the flow exchange so that two bundles can't exchange liquid. Once the liquid enters a bundle, it has to go all the way through. So the ABWR was developed by a bunch of companies to try and improve reliability and safety and reduce cost. It was a little bit larger than traditional BWRs. It was about 1,350 megawatts, and they tried to use reheat to help increase efficiency. Later, the SBWR was developed by GE, and that implemented all passive safety systems, so no AC power was required during an accident. And then later on, the ESBWR which was the economic SBWR, was developed by GE, and it was supposed to be an improvement on the SBWR with a little bit higher power and enhanced safety systems. The CANDU reactor was developed in Canada. The express purpose of designing this reactor was to use natural uranium as fuel to avoid enrichment. So it's cooled by either heavy water or light water, and it's moderated by heavy water. This is expensive, but heavy water is a very attractive moderator because of its small thermal capture cross-section. But it also means that we have a smaller slowing down power in the moderator compared to light water. So it increases the moderator to fuel ratio, means we have a lower power density and a very large volume for our core. But again, we can use natural uranium as our fuel, so that helps reduce the cost associated with the design. It does have a very complex, very high pressure reactor vessel. You can see the calandria is where the moderator is stored, and then we have the calandria tubes where the coolant runs through and the fuel is located. So there's also a lower operating temperature for this reactor, which has some materials advantages but reduces the efficiency. One of the main benefits of this reactor is you can refuel during operation. This is a diagram of one fuel bundle. You can see it's a little bit different than the typical square bundles we use in PWRs and BWRs. But you can actually refuel this reactor during operation. One of the downsides, though, is that this reactor has a positive void coefficient of reactivity. Now, the NRC requires all reactors built in the U.S. to have a negative void coefficient of reactivity, so we can't build these here. But they've been extensively used in Canada.